I would like to welcome you all to our Urban Geology webinar, which is co-organized by Czech Geological Survey and Norwegian Geological Survey on behalf of our bilateral project supported by Norwegian Grants and with support of Association of European Geological Surveys, EGS. Today's schedule is split in two parts. The first part will focus on urban geological modeling at geological surveys. It will last about 1.5 hours, and we will hear the presentations from Dutch Geological Survey, French Geological Survey, Finnish Geological Survey, British Geological Survey, and Polish Geological Institute. Then we will have a short coffee break, about 15 minutes, and then we will continue with selected cities case studies.
Okay, thank you, Jan, for your introduction. And I'd like to tell you something about urban scale subsurface modeling as we do in the Netherlands at the Geological Survey. My name is Jeroen Schokker. Some context of the work we do at the Geological Survey. For the shallow subsurface, nationwide systematic geomodeling has replaced traditional geological mapping. This means we don't make any paper geologic maps any longer. We only produce 3D geologic models. One of the key drivers for our work is the establishment of the key registry on the subsurface. So this is, you could say, a large database which by law government bodies will have to feed and consult. So when performing ground investigations, the results have to feed into the database, and when doing new research, government bodies have to consult the database. The idea is single acquisition and storage of data and multiple use. It does not only involve data points like borehole data, but also the interpretation of data in models. And this is nice for us as a geological survey, as we get a lot of data to work with, but it also increases your user expectations. We basically produce two types of models, layer-based models and voxel models. And this, to the right-hand side, is an example of one of our voxel models, Geotop. It covers the upper 30 to 50 meters of the subsurface in a resolution of 100 times 100 times 50 meters times 50 centimeters. So basically, these are pizza boxes. And these pizza boxes or voxels are contain information on the geological units, on the lithology, and on uncertainties associated with that. The panel above shows geological units in part of the Geotop model, and the panel on the lower panel shows the lithology, the lithological infill of these geological units, with the different colors indicating different lithologies. However, you also see gray blobs in this in these pictures, and these gray blobs, I get a pointer here, these gray blobs indicate where anthropogenic deposits are located, and these are poorly modeled in this model. You see where they are, but you don't know what they consist of. So basically, we make use of borehole information. We then do a 2D interpolation of stratigraphical surfaces, and within the boundaries of each stratigraphical unit or geological unit, we do a 3D interpolation of lithological class. So this is our national workflow, but what about the urban geology? To the right-hand side, you see a geological map of the Netherlands, and all areas indicated in black are covered by anthropogenic deposits. So this is quite a substantial area a substantial part of our country. And we see these kind of anthropogenic deposits and reworking not only in city centers like Amsterdam or Rotterdam, but also in other parts of the country. For example, where you have industrial areas or where there are major roads and railways which are founded on natural aggregates. We also have a lot of coastal reinforcements and dikes, like here, for example, and other landscaped areas and landfills. There are many reasons why the urban geology is special as opposed to the geology of the countryside. First of all, geological surveys traditionally avoided the urban areas when mapping, and that is still reflected in the amount of data and the quality of data we have in our database. Then, of course, there's the presence of these anthropogenic deposits or man-made ground, and also the presence of man-made objects. An important aspect is that the subsurface of built-up areas changes rapidly over time. So normally we work with geological timescales, but that's not possible in the urban areas. And data are often acquired before a human intervention took place, so they do not reflect current conditions. There are differences in data availability and acquisition. For example, we often have to make use of third-party data in urban areas, but also the demand for subsurface information is very diverse and relates to a lot of different areas of interest. And as a last item, the intense use of the subsurface in the built environment also requires very high resolution data and models. So our aim for the urban subsurface is that the urban subsurface will be covered in sufficient detail in our 3D geological models to form a reliable and indispensable source of information for a whole range of applications and stakeholders. And for the shorter term, we focus on a few items. First of all, we try to incorporate additional data types in our 3D modeling workflows to arrive at that higher resolution. And secondly, we focus on characterizing and mapping made ground, and I will come back to that aspect later on in my presentation. So in the remainder of my presentation, I will present some project results. First of all, a project with the city of Rotterdam. It has been established in connection with the Cost Suburban program. And the aim was basically to increase the possibilities to apply 3D geological models in cities, especially in the urban spatial planning process. And we especially focused on incorporating additional information from the city council to improve model resolution. So we made a model of the city center. And this is the borehole information we had available in our own database, cone penetration test data, which was also of use here. But then there was also a database in Rotterdam, and that was very nice also, and it also contained historical data, and it allowed us to increase model resolution. And here we see one of the results, geological cross-section. The different colors indicate different lithologies, different kinds of ground. And this is the original model. And here we have the detail we arrived at when incorporating the new data of the city of Rotterdam. So the resolution could be increased to 25 times 25 times 0.2 meters. So this means 40 times more voxels. It did not only provide more detail, but also give new insights. For example, when looking at this brown layer here, indicating peat, you can much better appreciate where it is continuous and where it is not. A second project we have been working on, and this is quite recent, is a project dealing with a river dike reinforcement. In connection with climate change, river dikes have to be reinforced, have to be made more robust. But there are several aspects that are of interest when thinking about the failure of a dike. For example, you can have piping underneath the dike, or you can have macro instability. And to be sure what the subsurface of the dike is before starting to reinforce, you need a good ground model. And one of these rivers, the River Lek, is built on complex Holocene geology. You see that here. Here we have the river dikes with, in yellow, sand. Beneath them, river sand, channel sand. But there's also a lot of peat in brown and clay in green in the subsurface. And the current model just does not do its job. So we needed higher resolution. And that was made possible by using, again, data that was not in our own hands. Here we have the stretch of dike, and to the right, we have here the red stretch here. And here we see all the data points that we have available. Not only our own data, but also a lot of CPT data from the waterboard, and a lot of hand core data, hand drillings performed by tens of years of student fieldwork in this area. So with this, and with the incorporation of all the CPTs, we could create a very large number of data points. The CPTs were interpreted using an artificial neural network to translate the CPT data into an artificial borehole. And we did this by training the neural network with 231 borehole CPT pairs. This is one of the results. Lower left, the original model. Upper right, the Lek river dike model as it is now. And here you see the river dike in gray, built-up areas here. So this model now has the resolution that is needed by the waterboard. Again, here the colors indicate lithologies. So in yellow there is the river channel sands, and then you see in this panel diagram the brown peat layers and the green clay layers and their interaction with the channel sand. All this information has been gathered and combined with other 3D information, like on the presence of trees, the presence of houses, the presence of subsurface networks in one 3D digital twin. And this digital twin was created to inform stakeholders and the general public. And information can thus be given not only on what measures are necessary, but also on why these measures have to be taken at that exact location. For example, if you live in this house just behind the dike here. But the work we are currently doing is focused on the modeling of anthropogenic deposits. These form the link between the natural subsurface layers and the above ground world. Characteristics and properties of made ground may influence model outcomes, and they can also be used to bridge the scale and information gap that exists between the natural subsurface and the above ground world. So basically, explicitly modeling anthropogenic deposits expands the scope of our models to the built environment. It's just necessary to incorporate those. Anthropogenic deposits are very diverse. They do not only consist of reworked natural deposits, an example here from an artificial island built up from dredged sand, but also a lot of non-natural materials are being used in the subsurface these days. These include waste, incinerator bottom ash, steel slag, recycled concrete, etc., etc. And it's very important to get to know the properties of these materials better. And it's really geologically significant these days, the use of these novel anthropogenic materials. For example, on the left-hand side, you see that secondary aggregates or industrial wastes already replace about 40% of the natural filling sand in constructions. And also, on a more global scale, there are really significant amounts of these materials that are being used. And last year we published a paper on that, which I can recommend to you all. So this is what we are currently working on, improving how anthropogenic deposits show up in our models. As a last slide, I have a few take-home messages for you. First of all, if you create high-resolution urban models, you require high-resolution data. This might mean using other types of data that you are usually using, or that you have to use data that is not in your own hands, but resides with third parties. Secondly, explicitly modeling man-made deposits is a key to link the natural subsurface layers to the above ground world, and also to increase the usability of urban models. An urban model is in many cases just useless if you don't include man-made deposits. And as a last take-home message, take into account that not many people are aware of what's beneath the surface, and out of sight is out of mind. So smart visualization, for example, the use of digital twins, might help to communicate subsurface information and subsurface issues to stakeholders and the general public. And with this, I'd like to end my presentation. Thank you for your time.
Thank you very much, Jeroen, for a very interesting presentation. Now I would like to invite our next panelist, Michael Boffils from Belgium. Thank you very much. The place is yours. Yes, we can see your presentation. Can we hear you, Michael?
Hello, everyone. Do you hear me?
Yes.
Sorry, I had some issues with the sound. So thank you, Jan, for this introduction. My name is Michael Boffils. I will share all of my screen so it will be more comfortable for you. Here it should be a full screen now. So my name is Michael Boffils, and I'm with Cécile Legrand. And together we will provide you what we expect to be an overview of what is urban geoscience at BRGM. So for the people that may not know who we are, so we are the French Geological Survey. It's about more than 1,000 people. Most of them are in Orléans or at home for the COVID-19. And as you can see, we address multiple domains as they are listed on the left, managing a lot of associated data and having several missions. So scientific research, of course, support to public policy development, very important for the urban geoscience or urban geology topic. International cooperation, mine safety, and training. So basically what most geological surveys already address. So when it comes to speaking about what is urban geoscience at BRGM, so we prefer the term geoscience because it's not only geology for us. So we wanted to give you the flavors of urban geoscience we have. Urban planning, geohazards, geothermy, water resources management, hydrology for urban planning, soil pollution, soil resources excavation, and also it address question of technologies. So we wanted to give you some taste of all of those flavors and it's not an exhaustive presentation, but we try our best to give you an overview of what we do. Just a small map, a tour de France of urban geoscience. So it's a focus on metropolitan France. Of course, it's about cooperation with the main cities in France. So you can see it's not exhaustive. It's some projects we identify on all the topics we address. So yeah, urban planning topics with some big cities and water resources management. It depends, of course, of where the city is and what are their concerns. So we will provide you some zoom on some of the projects we wanted to highlight. It's not yeah, just to say that we don't master every topics we are speaking about, so we do our best to give you a good taste of it, but we can also forward your question to our experts about this. So one main topic, it's about concerning urban geoscience, it's urban planning. And as you may know, we have a big project in Paris, so it's called the Grand Paris Express. France and especially Paris is supposed to host the Olympic Games in 2024. So we have a big project of underground infrastructure, extending the subway lines. And we have a project in BRGM in cooperation with the Société du Grand Paris about defining what is, I mean, the characterization of geology, hydrogeology, and also the geotechnical or geomechanical properties of the place where the subways will be. So very big underground projects. And of course, it's important to, it's deeply linked to urban geoscience. So now I will give hand to Cécile that will present other topics we address.
So do you hear me well?
Yes, we hear you.
Okay, thanks. So we also have projects on quite lots of projects dealing with geothermal energy. So to contribute to the energy mix in the biggest French cities like Paris, Bordeaux, Orléans. So there have been some work to assess the underground contribution to reduce the energy flow at city scale. So there has been a postdoctoral study, but there are also more local studies. So the objectives was to develop a conceptual models of energy systems, develop numerical models of underground heat transfers, and integrate it to cross-domain modeling of the urban underground. So an example of assessment of the heating demand coverage at city scale through geothermal heat pump with borehole heat exchangers is produced. And the figure shows the heating demand coverage for each municipality of a community. And at the moment, such development are applied to some cities to produce maps of heating demand coverage at city scale. So this is another subject deals with hydrogeology for urban planning. And this is the example of the city of Rennes, where intrinsic infiltration capacity was mapped through a multi-criteria analysis using natural criteria like thickness of non-saturated zone, soil permeability known on the rural part only, the potential presence of clay, the indices of development and persistence of water networks, soil hydromorphy, slopes, underlake zones. And this knowledge map has been translated into legal map. And as you can see, there is an obligatory infiltration on more than 66% of the territory. And of course, additional local studies are needed when the works are done later on. So that's it for hydrogeology. So still dealing with water, water resource management is also done in Lille and included in urban planning. And in this frame, there is long-standing partnership on water resourcing with the city of Lille. There has been scientific studies to better understand the behavior, quality and quantity of groundwater. Tools have been developed using hydrogeological models to manage the groundwater resource and the catchment for drinking water supply. So it takes into account, so it's very knowledge and management orientated. And at the moment, there is a new project, URBO, dedicated for urban planning, and it has an ambitious goal. It's to construct, model, and evaluate land use scenarios, allowing the sustainability of groundwater catchment for drinking water supply. So actually in Lille, there are water supplies in the north and the south of the city, and it has been a very, it's very dense city, so with lots of impacts. And so the metropolitan area is very, it's the largest in France. And so the urban planning documents cover an area of more than almost 650 square kilometers. And the population is more than 1 million of inhabitants. So we have quite lots of subjects dealing with water. In this case, it's the case in La Rochelle dealing with contaminated groundwater. And there were technical and scientific studies to optimize groundwater treatment. So this is a context of a polluted site, a former railway station of 30 hectares, which is close to the historical city's downtown. And it's impacted by different pollutions, including hydrocarbon, low non-aqueous phase liquid that reach the groundwater. And a redevelopment project is planned on this site. So to densify the site, densify the urbanization. And actually, the geological context is quite complex with highly fractured limestone, and the behavior of the pollutant is complex. So there has been geophysics investigation to evaluate the pollution plume extension and different pumping tests at different scale and timeline, coupled with geophysics to optimize, to evaluate the best option for groundwater treatment. And the treatment is going to take place next year. It's going to be pumping and treatment. On the areas, I don't know, to the most purple areas shown on the geophysical survey zone. So dealing with urban geosciences, there are also lots of subjects dealing with geohazards. Like here, it's an illustration of coastal risk in the Basque country, southwest of France. And the objective was to have a better assessment of the potential impact of groundwater on landslides in this urban area. So the monitoring occurs since 2007, and it deals with, it consists in a network of piezometers dedicated to water resurgence prevention. And so to the right, you have some maps locating the network. and to the right, the bottom, description of one piezometer. So we also, so you've seen in several present subjects the use of geophysics, and actually we're developing some urban geophysics tools. So for instance, dealing with shallow depth imaging. And so we developed no contact geophysical tools for continuous survey, like capacitive coupled resistivity, named OpenMapper, with the corresponding figure to the left, as you could see in La Rochelle. You also have MASW with no grounded geophones, gimbals, with an examples to the at the bottom. So that's seismic geophones that we just drive on the road. So that's a seismic geophone. We also developed urban deep geophysical imaging, and trying to so this is in development, to use seismic interferometry using urban noise. So this allows the acquisition using urban noise as seismic source, allows to provide signal processing. And so we aim to develop a permanent monitoring network using fiber optics, and also to develop processing algorithms using artificial intelligence for automatic interpretation.
So now coming back to me, a topic I'm more comfortable with. We are, in terms of technology, also working on the building information modeling topic. And we have a special involvement in geotechnics, and to define some standards for geotechnics at the BIM era. So you may know that there are existing standards for geotechnics in all the different countries, but when it comes to speaking about the BIM era and the possibility to connect to 3D modeling, 3D geomodeling, some work has to be done in order to make those standards enter the 21st century. And we have a creative project in France. It's called MINE, you may already know, and this work is going international. So cooperation between engineering companies, research organizations, infrastructure owners and constructors in order to have this kind of geotechnical standards. Our objective is indeed to define what are the main components of the subsoil or subsurface when it comes to describe geotechnical properties. So we have some action to define the vocabularies and to expose them through web semantics principle, APIs to access the data, and what we work on is to be able to navigate into the data. So you can see it on the bottom right of the figure. It's a way to access the geotechnical information from your BIM software. And this would enable you to have access to, of course, the characteristic of the subsurface, and to see how they're related. So what we expect to do is to show you how we come from interpretation to go back to the samples or borehole data that were collected. So you can figure how the model has been built, and it will greatly help to the update of this model. So this is how we do it, and in order we try to reach the international standardization step with the Open Geospatial Consortium, and we also have a collaboration with Building Smart International for this. So here we go to the perspective and conclusion. This was an overview of urban geoscience at BRGM. So of course we didn't speak about everything we are working on, but it's a lot of action, a lot of topic and a lot of people involved on it. As you may have seen it, we have some active collaboration with the city stakeholders. We have some scientific innovation and technological innovation we propose, something we develop in order to fulfill the requirements of those cities. So it helps us to go from thematic to integrated approach, but it's also about managing the data from their collection to the valorization, including modeling. So in those domains, of course, we must speak about 3D geomodeling. So it's this is our topic, how to combine geotechnical data or geological data with BIM on subsurface. We work also on geo modeling, of course, having our own tools that we maintain or extend. When you speak about urban geoscience, of course, it's about interoperability between all those domains of those topics in order to once again fill the requirements of the cities. So this is also why we have active participation in geoscience standards development through a different canal. And of course, these are opportunities of collaboration with other countries and cities, because this also experience and standards of technology we can share together. So thank you for your attention. If you have a question, we will be able to answer you through mails or something like that. Thank you again.
Thank you very much, Mikael and Cecile. It was a very nice presentation. I would like to encourage again all attendees to take part in our polls. You should be able to see the right button on the control panel, polls. We are publishing one poll for each presentation. So also I would like to thank all the attendees who already voted there. Now I would like to invite our next panelist, which is Hilka Kallio from Finnish Geological Survey GTK. Hilka, can we hear you?
Okay, hi. I hope you hear me.
Yes, we can hear you.
Thanks. I will now share the screen here. Okay.
Yes, it's there. Thank you.
Yes, and it should get to the full screen now. Yes. Okay, so thank you for having me here, and my name is Hilka Kallio. I come from the Geological Survey of Finland, and I'm a project manager in a project called Geo Models in Engineering Geology and Land Use, and also a member of Urban Geology Expert Group. And first, when I started to think like what kind of geological 3D models I will present today, so I really had to do some excluding work. There's a lot of different kind of models we are doing for different purposes. And I decided to concentrate for the examples we have done as a client assignments for the public sector, for building developers like municipalities. And I will leave out some of the models that are more like academic exercises still. So for that category goes to the structural geology and rock mechanics. And also, so there we don't have yet so much commercial projects going on. And then the low carbon energy solutions I will also exclude, because there's a lot of commercial projects going on, but it's an entity of its own and deserves an own presentation. So what I'm going through in my presentation are the ground conduction models of superficial deposits, what we do, then the characterization of fine-graded sediments, especially the sulfide clays and sediments of the coastal regions that used to be, I would say, quite overlooked issue earlier, but during recent years, so they have been taken into consideration much better in land use processes and land use planning. And the traditional modeling what we do are the groundwater area structural surveys and groundwater flow models. And first of all, I would like to go through some factors behind the geological 3D modeling approaches in our geological survey. So one important factor is the complexity of quaternary environment we have. So the layers in Finland, they are normally very thin. There are many rockhead outcrops everywhere, till and glaciofluvial deposits, and in between some fine-grained sediment basins. So to model this kind of environment, you need a lot of source data. And what we are lacking in our geological survey are the stratigraphical cross-sections and borehole logs, what many other European geological surveys have a lot in their registers and databases. But the data we have a lot is the geotechnical site investigations from the construction industry. And the areas, the not so urban areas, arable land areas, where there naturally is not so many geotechnical site investigations. So we try to cover as well as possible with geophysical measurements. And about the geotechnical site investigation data, so we have a large number of in situ tests, similar like CPT, cone penetration test, for example, but then we have just a few samples from the sites. So what we are doing at the moment, we are putting a lot of effort for the interpretation of the geotechnical in situ tests. It's a lot of work to do because there is so many of these drillings. And I would say at the long run, it's very unsustainable situation for us. So we are looking to the future and trying to find some solutions how to automate the interpretation work in the future. And one solution would be the numeric modeling with drilling resistance data, and of course machine learning of geotechnical profiles. And what I'm very proud in our country and about the data we are using is the data standard and the data storage regimes we have. So GTK maintains at the moment the largest site investigation register in Finland. So many municipalities, they are just happy to allow to us manage their data sets. They see it as a bargain. Of course, there are some large cities who want to maintain their own data sets and take care of the sharing, and it's okay. It's okay. The most important part is that it's stored somewhere and it's shared proper ways. No matter if it's our survey or the city administration. And we have also very nice harmonized data formats for site investigations. I would like to compare it to the British AGS format. So it looks different when you open the data file, but anyway, there is a lot of similarities. And I made some, I was comparing the British format and the Finnish format and found a lot of similarities and some differences. But here on the right side, I have an example of the most typical drilling method and drilling data from our register. So this is the Swedish weight sounding test. So you have here, the first column is the depth of the drilling. Then you have some parameters, weights, and number of rotations, and then some kind of an idea from the driller, like what is the soil type there. And so almost all the site investigation data fits to this format. We have there many different kind of drillings. There is in the middle is an example of undisturbed sample data, and then on right, water table level measurements from a groundwater well. And here is a screenshot from our site investigation register. This is an area from city of Tampere. So you see the drillings are quite irregularly placed in the areas. Or some areas there's a lot of them. So you see the scale here is 300 meter. So in a square, 300 meter times 300 meter, you can have like hundreds of drillings in certain parts, and somewhere you don't have so much. This is now a modeling example from city of Tampere area. So the city of Tampere, they were interested to know what is the infiltration rate of the lake water into the esker. So they are planning a landfill area, some man-made islands here for housing, new housing area. And they were worried like it will affect to the aquifer we have on the esker area. And they wanted to know what is the infiltration rate of the water from the lake to the esker. And the estimated, first estimated idea was like the infiltration will be 1,000 cubic meters per day. So they asked the Geological Survey to make their own estimation, and they also asked a geotechnical engineering agency to make their own estimation. And first I will show like the geotechnical engineers were doing. So it was very simple 2D finite element analysis. They made one cross section here at the shoreline. The cross section is shown here. They analyzed the soil types and got the result like 60 cubic meters per day, the infiltration rate. So this is much less than this first estimation of 1,000. So our geological survey made own modeling approach. We were modeling the whole aquifer system, first making the geological model. Here you see some cross sections of the area of the esker made with Groundhog software. And then we made, let's say, traditional flow model of the aquifer. And the result of GTK's analysis were that the infiltration rate would be 155 cubic meter per day. So it was funny to compare two methods. The very fast one made by the engineers and our method. It's hard to say which one is now more accurate, but at least the results have the results are on the same scale to compare the earlier estimation. So the city knows now that the infiltration rate is not that large as they were thinking from the beginning. Here is another model we made for the city of Vantaa. It's about the Quaternary Layer. So you see the modeling area, the large area here, and this area of a smaller version of the model. And so the model of the large area is not yet ready. I cannot publish it, but I can show this smaller part. So this is a very typical let's say Finnish southern Finland geological setting with some short deposits on the top, then clay, silt, fluvial deposits still, and finally bedrock. And we made two models, one with a geological modeling software and one with CAD-based modeling software for civil engineering, and compared the models. And here is closer look of the model one cross section there. So you see here are the data here is like all of the data is the geotechnical investigations here, and what we are doing the interpretation of the drilling resistance data to the geological layers. And we are also doing some ground condition modeling in different cities. This is an example from the city of Espoo, what we did. So the idea is to automate the process of interpretation by filtering only the essential information out of the digital data sets. And the results are quite promising, I would say. So the source data we were using are the site investigations, geological soil map, and digital elevation model. And with some GIS work, we could create this kind of ground condition map based on this classification, I would say rather fast. So there is a lot to develop on that side, but the first results are promising. And then this is my last example. I told you the sulfide sediments important issue at the moment, and in GTK we do a lot of research with them on many different scales, on national scale, on regional scale, and even on local scale. This is an example of assessment of the areas of potential sulfide clays. It was an assignment from the city of Espoo. So they want to direct their large-scale soil sampling measures to the areas where they see that the risk for sulfide clay occurrence is the highest. So it's about saving the money, that you don't have to make a big soil sampling program to the areas where there is maybe no risk at all. So, but anyway, so thank you. I hope you got a general overview now what kind of modeling work we do in our survey. Thanks.
Many thanks, Hilka. It was very interesting to watch your presentation. I would like to invite our next speaker, which is Tim Kiersey from BGS. Tim, can we hear you?
Yes, can you hear me?
Perfect, thank you. And we can see your presentation as well.
Fantastic, thank you. Just let this. Okay, well, thank you, everyone. And I'm going to be talking today about some UK case studies, about particularly highlighting, as others have done in previous presentations, the particular challenges and opportunities that exist when doing geological modeling in urban environments compared to from a sort of traditional environment. Okay, so I'm going to pick out 3 challenges and 3 case studies. So the first one is, again, following up with what Jeroen was talking about, how do we predict and quantify artificial ground? This is a particular challenge in urban environments, and I'll show you some work that some of my colleagues have done on that. The next thing, the next thing I'm going to talk about is scale and accuracy. So one of the challenges of working in urban environments, and again, other presentations have picked up on this, is that you're actually demanding a much higher resolution of accuracy of your models. So we think of a traditional hydrocarbon model, sort of an oil field model, that tends to have an accuracy of hundreds of meters, even though, I mean, they're usually working down to 5 kilometers depths. A traditional sort of regional survey model tends to have accuracies of about tens of meters, and that's our experience in the UK. But in that urban environment, you want to get to that plus or minus meters of accuracy, or less if possible. And then finally, I'm going to talk about how we're using 3D modeling to understand interactions of different deposits in the subsurface. Again, this kind of picks up on what other presentations have said. But one of the critical things about trying to do the roles for 3D modeling in an urban environment is actually using that model to understand how different units interact with each other. Okay, so I'm going to use 3 case studies. I'm going to use London to talk about anthropogenic deposits. I'm going to use some work that we've been doing in Glasgow on shallow geothermal to talk about scale and uncertainty. And then finally, I'm going to talk about a place called Grangemouth, which is just between Edinburgh and Glasgow, about halfway between those 2 cities, to talk about understanding link controls on subsidence in that environment. Okay, so trying to model understanding anthropogenic deposits in London. Now, London is a particularly interesting city because actually the centre of the city, the city of London, the old city of London, actually predates the nation of the UK. It's older than England as a country. So it's been there for a very long time, and a lot of London is built on not natural ground, it's built on other bits of London. So understanding and trying to predict that man-made deposits in London is critical. It's mostly built on other bits of London. The key challenge as geologists coming to try and understand anthropogenic deposits and predict is trying to create stratigraphies in them. Obviously, we're working on quite different timescales, and generally it can be quite confusing. How do you build a stratigraphy in this type of environment? However, sorry, so this is the City of London. Again, so this is the study that we're talking about here, I was say conducted by co-authors, colleagues. I wasn't involved in this study. The paper is at the bottom there. I absolutely recommend you read it. Is focusing on this the very center of the City of London. And what they found is what they used was using materials that you can find and were described in geotechnical boreholes in those engineering deposits to build an event stratigraphy. So using the very simple processes, the same way we build a stratigraphy in natural deposits, you can apply the same thinking to man-made deposits and then use that stratigraphy to try and understand how these deposits vary with thickness and time. So what they found worked very well. They looked at a whole range of deposits, but so a whole range of materials that have been found in boreholes, but what they found worked really well was concrete to pick up the stuff that had happened since the sort of really the 1960s or 50s and 60s. Ash and coal in London was a really good marker of industrial deposits. So this is the Industrial Revolution. So this would be 19th century and 18th century deposits. Brick is an interesting one. Brick has actually been used in London for a very long time. And in fact, is actually in some cases as old as Roman. So it's probably not as good a market in London for dating your deposits. In other cities, it might be more useful. And what they found was that, yes, the thicknesses of, when you date your anthropogenic deposits, you can then look at how those thicknesses change with time and with space. They also found that there was quite a strong relationship between the heights of the buildings and the thicknesses of the underlying deposits, and also where we had large over-thickenings of anthropogenic deposits over previous or historical watercourses. So basically these were areas where we had previous rivers that have been then built on and built over and culverted, and they actually, if you knew where those old watercourses are, that was often some of the thickest deposits of man-made ground. Okay, so moving on, I'm now going to talk about some of the work that I've been involved in. This is in central Glasgow. Many of you have seen the work that we've done in Glasgow over the years, but this is working on a new project, which is a BGS flagship project looking at trying to use trying to de-risk using mine waters as a geothermal asset. So what we had the opportunity to do here, this is part of a larger project called the UK Geo Energy Observatories. And what we had the opportunity to do here was to site some research boreholes in the centre of Glasgow to try and essentially tap into this mine working to geothermal. As many of you have seen, we have built a huge range of models in Glasgow over many years. Unfortunately, at this site scale, we realised our models were not good enough. So the image we see of the 3D model here is our city scale models. And at this sort of site scale, so this the view of the model is about the scale of the aerial photo. There was a lot of noise and variability on that surface, and the model was actually in this case, an accuracy of about 10 or so meters, vertical accuracy. So in this case, we employed some higher resolution modeling software. We used implicit modeling. This is using Secure GoCab, but other software, Leapfrog, does similar things to build this much higher resolution model with much more constraining data, and then using the power of the sort of more implicit geological field modeling to produce a much more accurate interpretation of the geology. And of course, the advantage of this is we got to test it. We had the opportunity, because this was obviously for a particular project, we drilled holes into our pre-drilled model and tested its accuracy. And what we found was that, yes, so this little panel in the bottom right, we can see the boreholes that we had drilled. And in the background, the colored stripes are the pre-drill model. And we actually saw quite good accuracy there. We were usually in about less than a meter, in some cases far better than that. But the two wobbly surfaces that you can see coming through there, they are the old GoCAD surfaces, the old regional city scale model. So again, it gives a feel for if you're trying to work in that site scale, you do need to start thinking about maybe using different methodologies or things that are a little bit more specific to a site scale. And as I say, we found the implicit methodologies work really well. Okay, so finally, I'm just going to give my final case study is another project that I've been working on in, again, in halfway between Glasgow and Edinburgh, a place called Grangemouth, which sits on the edge of the River Forth. And at that locality, we were interested in the fact that we knew from INSAR data that there was about 30 millimeters of subsidence occurring per year. And if you see in the bottom right-hand corner here, this is the LiDAR terrain model. And you can see these very odd features in the land surface. These don't look natural, they look like mine workings. However, we know that the site, mine workings on the site finished in the 1940s. So the question is, oops, sorry, and also in that area, we have 80 meters of glacial and glacial marine deposits separating rock head from the land surface. So what was going on here? We could see that we had what looked like ongoing mine substance, yet the mining finished 80 years ago, and we had a huge thickness of Quaternary deposits between them. So again, we used a lot of site geophysics, things like Chimino to improve the rockhead methodology, and a huge suite of EM and other sort of local seismic models to build a really high resolution constrained model here. And this is what we see in this top left-hand corner. And what we also realized was that we looked at the lithological composition of the overlying Quaternary deposits and realized we had a huge amount of clay. And based on previous work that had been done on this site, although they hadn't picked up this substance story, we realized that that clay was what's known in the industry as quick clays. These are glacial marine clays, which are quite famous for being able to landslide in very low angle slopes. There's been some quite significant landslides in Norway that have happened as a result of this. And what we think has happened at this site, and what we could use the model to determine, was that the mine subsidence that had happened in the underlying coal measures had then brought these quick clays into contact with seawater. And this is one of the main trigger mechanisms for destabilization of these deposits, is sort of changing the salinity of them. And it was actually the subsidence that we think might have caused that. Now, what we now know is that this is potentially quite a significant hazard. So all of these areas highlighted in orange here are areas where we know we have coal workings quite close to the surface, and we have mapped marine clays. So we've actually identified a hazard that we didn't even know was there. Probably not actually going to cause a failure like what we see here in Norway. However, if we start to use, to do geothermal with trying to use the mine workings below these deposits to do geothermal, there is a potential hazard there, which again, we probably wouldn't have recognized unless we had the model to allow us to realize how these things were interacting together. So, just in summary, so 3D modeling is critical to understanding urban geology, and accuracy is really quite important for the stakeholders. We found that, particularly trying to get the resolution at the site scale, the implicit methodologies that are sort of becoming more accessible are actually really good at giving that sort of site scale accuracy. And I think what's interesting is that it often requires using traditional geological understanding, like what my colleagues did in London, to understand non-traditional problems like anthropogenic ground. So I hope that's giving you a bit of a flavour of what we've been doing in the UK. Thank you very much.
Thank you, Tim, for the presentation. Thank you very much. And now we are moving to our last panelist of the first session, which is Grzegorz from PGI. Can we hear you?
Yes, hello.
Thank you.
Share my screen now. See my presentation?
Yes, it's there. Thank you.
Do you see my presentation?
Yes, we can see.
Okay, I give a full screen.
Thank you.
Do you see full screen now?
Not yet.
One moment. And now?
Yes, it's there.
Okay, so I would like to, my name is Grzegorz Ryżyński. I'm from Polish Geological Institute. We are a Polish Geological Survey, and I prepared with my colleagues Edyta Mayer and Krzysztof Mayer a presentation about our flagship project, which is Engineering Geological Database. And I will try to show you what we are doing and few case studies of application. As other presentations, I must change the slide. Okay. As in other presentation, we saw mostly 3D application. It is essential to do good urban 3D modeling. We need a very detailed data. And our database is aimed to gather all the urban geology data, which is gathered in geological archives. We have started gathering this data in 1998, and since now we gathered 400 boreholes and over 65,000 geotechnical parameters in the places where samples were taken for the biggest cities in Poland. And we made already 15 cities. Those are those which are in green color. And we currently are in progress for Lublin and Szczecin. Those are red, and yellow are under a feasibility study. The data we gather is mostly boreholes. They are available by a bookmark, budownictwo. One moment. You see a link there. And we distribute the boreholes. One moment. One moment. I have a technical problem. 1 second.
That is fine. Thank you. Take your time.
Okay.
Yes.
And we present the boreholes which are available in our database. You can download the borehole card. Also the samples which are gathered in a database. Another layer is geomorphology, where you can have information about the geomorphological units which are essential for the determination of genesis when you do a digital 3D modeling. Also, the digital elevation models are for the cities are recalculated for the land slope maps. And finally, the all borehole data is reclassified in an engineering geological layers map, which allow us to determine the maps for at given depths from 1 to 10 meters, which are for the lithostratigraphical and genesis service like group. We use a stratigraphic criterion and a genesis criterion, and then give an information about the cohesivity, if it's cohesive or non-cohesive soil. And the data is presented, as you see here, in the form of those like mathematically generated squares. It's a geoprocessing done by a method which is called Euclidean allocation, because database is very heterogeneous and the quality of the data which is submitted to geological archives is very different. We cannot do very, let's say, sophisticated modeling, but we give just a quick geostatistical presentation of a database, which when someone later uses the cadastral data, it's a preliminary data visualization. It's not an interpretation, so the other interpretations can be done later. The same is done with the first encountered groundwater. So this geostatistical interpretation is presented, and other thematic maps are included in the database, which are available for the all mentioned cities. It's natural hazards map, which is for including the occurrence of low bearing capacity soils. The anthropogenic hazard maps, which includes the occurrence of anthropogenic soils and the boreholes where the mining cavities are encountered, and a dedicated maps for the cities with mining hazards. It's a mining hazard map where all information about boreholes with mining cavities and the isolines of a predicted mining settlements are synthesized. And the final product of this database is a traffic lights map, which summarizes the good, medium, or bad foundation conditions, which is for the end users, which are like city planners or non-specialists. And this is the basic set of data, which is given to all the users. And the main issue in our project, which was finalized in 2018, was standardization of a borehole database, because the data set was very heterogeneous, and through many years the data standards were changing. We gathered all the boreholes since 2018 in a one database, which is a GeoStar standard. It's standardized, as you see here, in projects, boreholes, profile logs, and samples. Also, we keep in the database soundings. And we added in all 400,000 boreholes the innovative syntax that the symbol of a soil, which can be very complex, is separated into numerous parts, like main component and some interbeddings or additives, which all are have defined vocabularies. And for modeling, it's essential that lithology is codified and stratified. It's similar, like in a presentation that was given by Hilka. It's essential, so we try to make our codes compatible with the AGS standards and give the open documentation on the website for the data which is stored in a database. The same is done with the engineering geological series, genesis codes, and stratigraphy that allows the user to freely create his own subsets of data and reclassification. And also the 30 spatial layers, which are consistent for the whole country and are the same in the city, to facilitate further applications in BIM or any other processing by external companies. We created 30 defined spatial layers, and all the documentation for those layers is presented, and it's essential for BIM users to have this kind of documentation. And case studies, when we have this data in cities is essential for visualization for large city infrastructural projects. That, for example, in Warsaw, we have a nice case study of application of our database, that in 2012, there was a construction of a second Warsaw metro line, and on a C11 station, it was Świętokrzyska Street, we had a situation where we had a geotechnical failure, and the mixture of sand and water gave a hydraulic failure from the bottom of excavation pit that destroyed the foundation of 2 nearby buildings. And it was a very big obstruction of work. there was a group of geotechnical documentations done, and there was very essential to create a map, not in a site scale, but in a broader scale, surrounding the area, showing the discontinuities and the shape of a Pliocene clay roof, and to identify the area where the hydraulic failure had place. And our database was used to create a broader model on demand, and it was essential for visualization of a Pliocene clay glaciotectonic deformation. The second case study is also connected with a Warsaw metro line, that after first and the second metro lines were constructed in 2018, there was idea to construct a very big skyscraper just above the crossing of two metro lines, and the identification of the geohazards at the beginning of the feasibility study for this construction also required the broader model, not only in the site scale, but bridging the gap between 1 to 10,000 scale, like urbanistic and more geological scale materials, with a site scale data essential for planning of this kind of construction. And we see here also that this visualization of a Pliocene clay roof deformation allowed the project manager to convince the budget planning and economic department to book more money for geology, to have more dense placement of boreholes, to more detailed determination of geological conditions. Another example of a bespoke maps is a case study 3. It was done for Bydgoszcz Waterworks company when they needed specific maps that Bydgoszcz city has all the maps I showed you, which are maps that are predefined, but they have a special needs. They needed a map of permeable sands occurrence up to 3 meters below ground level to determine the infiltration to groundwater. So this kind of map was possible to have this kind of map generated very quickly thanks to our innovative syntax in our database, and also map of Pliocene clay occurrence and areas of gravel beds occurrence, which was essential while creating a micro tunneling for waterworks. So the areas of occurrence of gravel beds was essential to find them in the database. So the filtering of database allowed to create this kind of map just on the fly. And another case study is how our database is related to BIM and CIM, the city information modeling. We gather the data which is essential for feasibility study. And as BIM and site investigation is focused on a building site scale, we try to move it towards to city and quarter scale and focus on GeoSIM, so on the underground. And the main problem is that the data, it's not reused, and all contractors that do site investigation use different standard of digital data storage. So when there was opportunity in 2018, we made the guidelines, new methods of soil investigation in roads engineering, which was implemented from a research project by a general roads and highways directorate. And they used these guidelines to determine a predefined geological data exchange workflow between investor and contractor. That usual approach that was to prepare this kind of hard copy paperwork, very much amount of information in a form of printed documents, was prepared in a very defined digital copy with reference tables, allowing to identification at which stages of design, which kind of geological investigations are being made, that allows them to create a database that is growing along the progress of the construction process. And as you see, the data that's, for example, that's highway ring road of Warsaw, you can see the points from the preliminary databases like our engineering geological databases and resources. And during design, this all process is merged, and then this data is available for reuse and for storage in our database. And all the vocabularies and all the codes that are implemented in this document are relevant and compatible with our engineering geological database codes. So we go towards the standardization that we saw it's already made in Finland, but in Poland it has been not made. And this kind of actions are essential for further 3D modeling and efficient generation of models. So our recent activities are focused mostly on data structures and for promoting the data model, our data model to other companies and entities to organize a geological data exchange framework. So that's more or less our activities. So thank you, and this is the last slide.
So many thanks to Grzegorz and also to all our guest speakers of the first session. Let us have a 15 minutes coffee break. However, this time we have to make it ourselves. So let's meet 5 minutes after noon, Central European time. Thank you. Okay, I hope that we are all back from the short break and that we are looking forward to the next session, which will focus on city case studies. In the current session, we will hear presentations about selected cities, which will be Oslo city in Norway, Manchester in the UK, Nantes in France, and finally Darmstadt in Germany. I hope that we are all connected. The first speaker will be Ingelof Eriksson from city of Oslo. Ingelof, can we hear you?
Yes, I'm talking now. Do you hear me?
Yes.
Very good. I'll start sharing my screen.
Yeah, it's on. Perfect.
Yeah, do you see it in showing mode?
Yes, yes. Thank you very much.
Thank you. Then I'll start. So I'm Ingelof Eriksson. I'm the municipal geologist of Oslo. And I've been having this position since May 2019. So very quickly about the city of Oslo, which is the capital of Norway, situated in the south of Norway. Everything that you see within the red line of this map of the city of Oslo is what we call the building zone, and where all the building in the city is taking place. The rest is a natural reserve area. And the population of Oslo is currently 694,000 inhabitants. And the forecast is that it will grow, but it was quite interesting when I was looking at the numbers the other day. In the last 4 months, there had actually been a reduction of 500 inhabitants in the city. So that was the first time I've seen that. Okay, going a bit fast, sorry. We have done what we call a mapping of the resources and the challenges of the geology of Oslo. And the main resource is the volume situated under the ground, used for transport infrastructure, technological infrastructure, or storage, for example. We also have some difficulties with the geology. We have quick clay, as was mentioned earlier. We have polluted soil, as most cities, or all cities. And we also have alum shale that is difficult to build in and creates polluted waste whilst moved. Just quickly, what information we have? We have some maps generated by the Geological Survey of Norway, like bedrock map and Quaternary Geology map and other geological maps. We also have some maps generated by the Norwegian Water Resource and Energy Directorate. They are also responsible for the mass movements and eventual landslides. And we also have our own, what we call underground archive, which is a semi-digitized archive with about 200,000 geotechnical drillings from various times and of various quality. And we also have a national database for geotechnical investigations, which you can see some images of here. And you can see we have a lot of boreholes in Oslo. And I would say that almost all of them are generated from our local database. And in the national database, you can only see where it has been drilled. You have to go to us to actually get the reports, and you can get the reports as PDFs. We also have newer drillings that are taking place, are mostly given into the national database. But for us as a municipality, it's a bit difficult because you need a program called GeoSuite to actually open them up and see them, which we don't have at our, which we don't have in the municipality. So some of these newer drillings and geotechnical drillings are not really available to us, but they are available to consultants, for example. We also have a groundwater database, which is an historical database with some 74,000 measurements of groundwater, and they're all taken or measured during development projects, such as tunnels or large buildings. We also now have several tunneling projects finalizing or starting up in our municipality, and they are measuring groundwater and having groundwater programs. So we are aiming to be able to collect the data from these measurement programs into this database. So it's in the working. So a little bit about how we work to get the information about the subsurface into the planning process. And we know from before that if we use the full potential of the Norwegian Planning and Building Act, future use of the subsurface will be more efficient. But we have to do it and use the potential we have. This schematic overview shows the possibilities of the planning levels and the processes each level has to go through within the Norwegian planning legislation. This is only for municipal plans. We also have regional plans and state-induced plans. We have a municipal master plan, which is the master plan of the municipality. We can also make municipal subplans, which can be either a theme or a specific area of the municipality. We also have area zoning plans, which are smaller areas, but bigger areas than the detailed plan. So it's to get a more homogeneous development of an area. And in the end, we have building applications. Between 2013 and 2017, we had the subsurface the underground project, which produced a report and an action plan. And the action in total has 21 actions, or some more, I'm not doing the counting right, and is built up on 4 different legs. We need to have sufficient legislation. We need to ensure availability to information and data at the subsurface. We need to manage and use the subsurface information, and we need to plan and use of urban subsurface. And the following examples I will show you will be examples of how we work with this action plan. Since 2015, we have a municipal master plan that takes the subsurface into account to a small extent. We have zones requiring special consideration. These are the red zones that you can see. And the red ones are hazards, such as flood or mass movements or derelict ground. But basically it is to ensure the volumes of future rail tunnels or existing rail and metro and road tunnels, sewage, fuel tanks, and so on and so on. What we're doing right now when it comes to strategic planning is what has felt like taking 2 steps forward, no, 1 step forward and 2 backwards. We started up an underground master plan project in 2019. We had a budget, a project group, and we're in the making of this project, which had very ambitious ideas about actually investigating the possibilities to produce a 3D plan in Oslo, which you can see some images of down here. We were also very inspired by the Finnish underground master plan. But during the summer of 2020, we had to stop the underground master plan project due to economical reasons. The funding was withdrawn. And now in November 2020, I'm coordinating an underground resource group in the land use element of the municipal master plan. So what we have done is we have downscaled the ambitions from the underground master plan project and put it in to our municipal land use element of the municipal master plan. That is in the making right now. So the timing is right, which is good. We are planning to have 6 themes: use and protection of the subsurface, groundwater, risks in the subsurface, masses, like rocks from tunnels, what do you do with it, etc., etc. Resources in the subsurface, energy from the subsurface, for example, and data and information. And data and information is the first thing that we need to do is actually investigate if our legislation admits us to have demands for data, sharing of data and information in our municipal master plan. Here is just a map that is an example of what we kind of like to create on a strategic level. And this is about the possibilities or the risk for settlements. On a lower level, area zoning plan, we are working on a project to study surface water and ground conditions in urban planning. And we have been granted some 35,000 euros that we are using to digitize geotechnical information from our Geotechnical Archive in a very manual way, not as high-tech as we have seen in the earlier presentations. We then produce maps to use in communication with urban planners. And the good thing with this project is that we have had a cooperation with the urban planners from the start. So we've already discussed a lot of the difficulties of the ground conditions in this area, because this area is very complex. It's in the middle here is an old deposit, an old landfill from the waste of Oslo. And along here, we know that we have quick clay, and also depth to bedrock is at some places 90 meters. So it's quite an interesting area that we found here. We'll also organize workshops between urban planners and specialists, and produce a library of surface water solutions in areas with difficult ground conditions. I'm not very much involved in that one. And then I'll show you some examples of 3D modeling that we have. And this, the first model I will show you is very much on the lowest level. And it is a large tunneling project that we have, Fornebubanen, which is a metro tunnel that is about 8 kilometers. And there is one BIM model for the tunnel and the surrounding geology, and there are detailed models for the stations and the similar areas. It's also worth to mention that there is a water tunnel that will cross somewhere around here, I think. There is a metro tunnel being planned to connect to here. There is a train tunnel that will come here somewhere. So there is a lot of activities in the making and in the planning in this project. The images of the model has been in production for about 3 years. And you can see on the top here, you see the tunnel in blue, and the red areas are weakness zones in the rocks. And here is a detailed view with a weakness zone that is known from other tunnels. And the blue part here on the tunnel is where it is estimated that it is needed to be completely waterproof, the tunnel construction. And the model is based on results from geotechnical investigations that exists from before, core drillings executed during the project, data from existing tunnels and old reports from those tunnels, a lot of reflection seismology, and ground investigations and field work. And I think there is an estimation that the value of this, of just the field work, is about 10 million euros. So it's a lot of money that has been invested in this model. I couldn't get a specific number for the geological part of the model because it's all put into one budget of the model. Some more images and some details about the programs used. And as you can see, there is a lot of different programs and such a detailed BIM model, of course. And what's interesting when I've been putting together this presentation is that we are now here in a very detailed area, and also the design, final design of the tunnel has actually been made in the making of this model, which means that in some areas, although the detailed plan has already been decided, there will be areas where the detailed plan will need to be changed due to the information collected and the decision taken upon the model. But what is interesting is that the developers have different capacity to manage BIM models after construction is complete. I mean, here we have a 10-year project, but we need to start thinking about who is going to manage this BIM model after the construction is complete, and will there be geological information from the model that will not be considered interesting to keep in the model, and how do we ensure that the geological information from such a nice model is actually possible to share and reuse after the construction of the tunnel. I know there is a lot of cooperation between the projects, the tunneling projects going on, but also lifting it from above project level and seeing kind of the whole picture is striking me as very important now, and start planning for this as early as possible. We also have our Geotechnical Archive, as I mentioned. We have done some non-high-tech digitalization of it, created, this is 3D model that was made by Cecilia in 2015, I think. And now Michelle, who's managing our Geotechnical Archive, is working on another program to make models from what we have digitized. And also, I know that the new water tunnel that is being built, which is one of these tunneling projects that I mentioned earlier, will use the program Leapfrog to model geology. So basically, we have a lot of different models coming up in different programs, and that will be interesting. Just a quick idea, because from what I see in strategic planning, how much 3D modeling do we need? The easiest way to communicate a difficulty is probably by very simple maps like this one, which are the red dots are quick clay that has been that we know there are quick clay, and the orange dots are clay, just normal correct clay. So just finishing off with some Christmas wishes, we're almost there. I wish that data and models are kept, stored and made available. And I very much agree on the standardization part of this. It's important. Politicians and other decisions maker needs to see the big picture, not just project by project, but actually allow us to keep, store, and update models. And geological competence should participate in early decisions of large projects, and they are made very early. As far as I can realize, probably earlier than the municipal planning regime starts up. Thank you very much. That was all from me.
Ingelov, for a nice presentation from Oslo City, and also thank you for your Christmas wishes. I got a bit scared when I heard Christmas so early. Yeah, they are close. The next panelist is Stephanie Bricker from BGS, who will present Manchester City. Steph, can we hear you?
Hopefully you can hear me.
Yes.
And I will just try to share my screen with you.
Yeah.
Hopefully you can see that in presentation mode.
Yes.
Excellent. Thank you very much, everybody.
Yeah, now, but sorry, now we can see like the control panel for the presenting. Maybe can you switch in display settings that we can see the presentation?
That should be right now.
Wait a minute. Yes, it's there. Thank you.
Thank you. I'm Stephanie Bricker. I work at the BGS leading our urban geoscience programme and have the pleasure of being chair for the European Urban Geology Expert Group at the moment. Today I'll talk about a case study for Greater Manchester, and my particular thanks to my colleagues who have all participated in the projects that are going to be presented to you. So I'll start by just talking about some of the drivers for urban geoscience, provide two examples of our work, one on brownfield land and one on sustainable drainage systems, and then I'll just finalise with a few key learnings. So our approach for integrated urban geoscience research is to think about the impact pathway from the research to delivering benefits. And often as scientists, we tend to focus more at that early stage of that pathway, to the science that we do and the outputs that we might produce. And I think for our projects to be successful, we want to also be focusing on the other end of that impact pathway to think about how the science is going to be used and what benefits it's going to deliver to our stakeholders. And to do that, what we want is a strong science evidence base at the starting point, but to think about industry needs and in particular relevant urban and environmental policy. And ideally, we want to be working directly with the owner of the problem so that what we are delivering is suitable for our stakeholders. Before I get into the detail, I want to share some findings from our PhD student, Catherine Ascott, who is looking at how the use of geological resources can support more sustainable urban design. And as part of that process, she's been interviewing stakeholders who are involved in some of the large regeneration projects that are using geological resources. And I might ask this question to you all: what do we think their biggest considerations were? And I can tell you it wasn't geology. Their primary considerations relate to the cost of the project and how it's going to be financed, how they manage risk and uncertainty, and how they fulfill any relevant policy obligations. So obviously geology plays a part in all three of those, but as the geological community, it's up to us to be able to present information in a way that is translated for their key concerns. Catherine also looked at what are the key enablers. So what enables a really successful project? And quite reassuringly, some of the sort of overwhelming responses were about collaboration, communication, and delivering multiple benefits through your project. So if we look in detail for Manchester, I think this is a nice starting point. It's a good quote that we often forget that the geological history and the general history of the land is a really important guide to how we use our city in the future and what we can implement. So if we orientate ourselves to Greater Manchester, it's the second largest city in the UK with a population nearing 3 million people. And despite a thriving city centre, there's actually a high proportion of the population live in what would be classed as socially deprived neighbourhoods. It's a city that's earmarked for lots of growth and regeneration through new transport infrastructure and new homes, and actually will be a crucial city if we are ever to balance up the economy between the south of Britain and the north. And a lot of funding has been set aside to help Manchester deliver to these aims and to implement the new housing and infrastructure projects. But first, if we consider the past and the industrial legacy in Manchester, again, it's a very, very old city. It started out as a small town in the 1700s, and it really grew up around the textile industry, in particular cotton, and all of the industries that are associated with that. So the chemical works or development of the transport routes to move goods around, to the point now where we've seen lots of phases of growth and regeneration and new infrastructure planned, which will of course be built on top of those multiple phases of development within the city. If we consider the geology for a moment, this is a map of the Quaternary geology. It's an environment that has been glaciated in the past, so it's dominated by till deposits, which you can see in the blue, and glaciofluvial sand and gravels, which are shown in pink. I've included a cross-section here from one of our earlier 3D models, and it just sort of demonstrates that the surface geology only really hints at the levels of complexity that you see with depth, both in terms of the lithology of the units and in terms of thickness, where we see deposits of up to 40 meters, which for the UK is significant. Underlying that Quaternary geology, the bedrock is equally complicated. In the north of Greater Manchester, where you can see in the greys, we have coal measures and an associated legacy due to mining in the region. And in the southern area of Greater Manchester, these orange and pinks, we have Permo-Triassic sandstones, and that Sherwood sandstone group forms one of the most significant aquifers for groundwater supply in the UK. So we have quite a complicated shallow geology on which we're building. And I want to show the relevance of that for our first case study, which was looking at a brownfield ground risk tool, which is led by my colleague Darren Barrero. And I want to return to my earlier point where I was suggesting we really need to think about the problem and we need to think about relevant policy. So in the UK, we're expecting to be building 300,000 homes a year. And the problem with that is that about 1 million of those homes are expected to be built on brownfield land. To help with this, local authorities or the city authorities create a register of brownfield land sites, and the Homes and Communities Agency, now known as Homes England, have developed guidance to help us estimate likely remediation costs based on geo-environmental information. So what we need to be doing is looking at the cost ratio in the business case for sites that are coming forward for housing, and whether there is sufficient economic case for the commercial sector or private sector to develop that land. And where that case can't be demonstrated, Homes England have a land fund to help bring those sites forward. So the solution here is having a better understanding of the financial viability of brownfield sites within Manchester. So we've been working on producing a brownfield ground risk tool, which uses a series of 2D and 3D geological and environmental data. And it provides two key elements. It looks at ground risk and it also looks at likely costs. And it does that for both land contamination, so the risk of associated with contamination and likely remediation costs. And it also looks at risks associated with geological hazards and costs associated with having to modify your foundation design because of those geological hazards. And it's really important that I point out here that this tool is not intended to replace any detailed site investigation. That's still expected to happen. But what it does allow is the local authority, in this case Manchester, to use it within their local development plans and spatial framework to get a coherent overview of all of the sites within their district. So the tool itself considers four main elements: how the land has been used in the past and what it's going to be used for in the future, what the risks are to the water environment and what geological hazards are present on site. So that's using the available geospatial data and maps and models that we have within the BGS. So what we then have, we present a web, well, in some cases, a web map tool or a map that is compatible with GIS systems to provide a risk score and costs where appropriate for all of the sites within their register. And this enables Greater Manchester Combined Authority to say which sites are financially viable and are likely to be brought forward by the commercial sector, and which sites are likely to need investment from their land fund. The next example I'm just going to briefly introduce to you is looking again at the financial case for sustainable drainage systems. So if we start with the problem and the related policy, back in 2007, the UK experienced very severe floods. They were summer floods associated with surface water flooding, not fluvial flooding, which cost particularly the insurance sector a huge amount of money. And in response to that, they introduced new policy, the Floods and Water Management Act, which required any new development to consider sustainable drainage systems and in particular infiltration systems. The other consideration is that as we are becoming more urban, we're increasing our grey cover, so pavements, car parks, roads, etc. And in response to that, the water company in Manchester increased the amount that they charge for managing surface water runoff from properties, and the amount that they charged was based on the percentage of grey cover. And on the face of it, that seems like a sensible idea, but what it meant was that lots of schools and health sites, so the NHS sites, saw massive increases in their surface water bill. So the solution that was proposed was, can they implement sustainable drainage systems on their site? They would reduce the amount of grey cover within their property and therefore lower their water bill. And can they use the savings that they're making on their water bill to pay for the cost of the sustainable drainage system? So this was a project led by business in the community, of which we were one of many partners. And it was asking three key questions. Where is it possible to put a SUD system in? Where can they save money on their water rates? And what additional benefits could be realised in the process? So BGS was involved in answering this first question, where are SUDs suitable? And we have a geospatial mapping tool which provides information about the infiltration or drainage potential, the vulnerability of groundwater resources, i.e. you don't want to infiltrate where it's being used for public water supply, whether by putting a SUD system in, you're increasing the risk of geohazards like land instability, or where there are significant constraints, like, for example, if you're in a flood zone. So we identified where it's possible to put SUDs in at the school sites. Then our colleagues in business in the community and in CLASP produced the economic model. So it was looking at where can savings be made on the water bill and how long or how many years it would take to collect all those savings together to pay for the SUD scheme. So in the graph, we can see the number of schools and NHS sites that would pay back over a 5-year period, 10-year period, and 15-year period. And then the final stage of the project was to look at the additional benefits. So we were helping with mapping here in terms of where the surface water flood risk is highest, which parts of Manchester have poor air quality or are more socially deprived, where they would benefit most greatly from putting in the subsystems. So just another example of where geological information can be used to help answer other related questions in the city. So just to finish off, some key learning points for us with our urban projects in Manchester. A good science evidence base is a must for your starting point, having good data, maps and models, really focusing on how that information can be applied and deliver on the ground impact. And that can only really be done by working with others in the city. And finally, just a reminder that we need to collaborate and communicate at early stages throughout these projects. And I think that's a key theme in lots of the talks today. And thank you very much.
Thank you, Stephanie, for a nice presentation about Manchester City. I would like to drive your attention before we move to the next panelist on the current poll question, which is about your opinion. How much attention does the underground or geological condition get in your city? It's quite interesting. Currently, we have that 25% of all the voters voted that it's like sufficient from 25%. So please, I encourage the rest of the attendees to take part in the voting. And now I would like to move to the next panelist, which is again Cécile from Belgium. Cécile, can we hear us?
Yes, I can hear you. Can you hear me too?
Yes.
So I just kind of share my screen. I have to click on that button. Do you see it?
Yes, currently not in presentation mode. Yes, it's there. Thank you.
Okay, thank you. So I'm going to present you a case study from the city of Nantes, but with a focus on one particular subject, which is the 3D geological models, including a typology of anthropogenic deposits. So the context, like in other cities, is the fact that urban redevelopment occurs, and due to an increasing pressure on urban land, due, for instance, to population growth, but also to city attractivity. In this frame, we have to limit urban sprawl and thus to rebuild the city on the city. So this means densification of urbanization, and like in the case of Manchester, we have to rebuild on brownfields. So this means that we have contamination problems to face. These contamination problems come from the human activities, but also they can come from the anthropogenic deposits themselves. And urban redevelopment also generates large amounts of excavated materials. And therefore you have to also anticipate contamination problems. So actually the reuse of excavated subsoils is a key stake for urban redevelopment in the frame of sustainable management. And so to optimize the use of subsoils, you have to include them in a circular economy, and to avoid repercussions and to anticipate the management of excavated ground with all the economic and environmental issues that are linked with. So you also, when reusing the excavated subsoils, you also have to avoid repercussion of soil degradation on human health. But as we've seen before, there are some difficulties to model or to spatialize these subsoils due to heterogeneities, discontinuities, and dynamic evolution. So to anticipate the reuse of these excavated subsoils, as large areas are being redeveloped, there is a need of a strategy at territory scale to assess the excess and lack of volumes and their qualities, to see the potential becoming of these excavated materials and the associated cost. It's also necessary to anticipate the contaminations, and therefore it's useful to have knowledge on the structure and quality of subsoils and underground through 3D models to assess the volumes and quality. And it's also the potential sources of contamination need to be known too. So actually we developed, we worked on several case studies on research and development projects, and developed a methodology for this. So we have worked on that subject in the city of Nantes, in the eastern part of France, but also in Marseille. And I will focus on the work carried out on Nantes. We've worked on 4 quarters represented here that are being redeveloped with surfaces from about 100 to 200 hectares. So I put A, B, C, D to help understanding the future figures. So one particular development we made in Nantes is we developed a typology of anthropogenic deposits according to their intrinsic contamination potential. And for that, we used the terms present in the borehole descriptions. And in particular, we distinguished 2 group types of anthropogenic deposits that might have intrinsic contamination potentials. The first one that we called questionable ones contain materials like industrial materials, like bottom ash slags, smelter, with terms like smelter. They also contain terms like tar, coal, pyrite, bitumen. And also we used the color descriptions, organoleptic descriptions, like black, except if it's peat or natural organic layer, purple, burgundy, so which is that occur frequently, like in this photography to the left. You see these black materials, like a layer, with some of these words being found in the description. Another type is what we call the various ones, which correspond mainly to demolition materials containing bricks, concrete, masonry, block, pavement, etc. So to validate this typology, we compared with the geochemical analysis. And so here you have in red all the questionable type, in yellow the various type, and it's compared to the yellow made grounds that correspond to natural materials. In this case, it's sandy materials coming from dredged sediments from the Loire River just nearby. Here it's the case of, it was developed on the North Island, which is the A case. And underneath you have alluvial deposits. And what we can see here is that you have for a selected trace metals, trace elements like copper, lead, and zinc, you really have the higher contents in the questionable type and lower, but still quite high contents in the various types, and much lower contents in the alluvial deposits, and even lower in the dredge sediments. And you also can, we can also see some geogenic trace elements like barium and nickel in this case, which are much higher in the alluvial deposits. So in this case, we have a specificity with the PCB that are higher in the demolition materials. So we used this typology to build a 3D model, and for that we used the available data like mainly geotechnical and coming mainly from geotechnical and environmental studies. So we used borehole description and physical-chemical properties. All this was put in local database linked to national ones. And for the interpretation, so we developed a stratigraphic pipe, both geologically and geochemically relevant, to build the geometry and structure of the materials, so including this typology. So anthropogenic deposits don't have a clear, simple logic of deposits. So we just simplified the representation, considering the width of the layer containing the worst, the more potentially contaminated typology, so that we always have the questionable ones above the various ones above the sandy ones. Oh, sorry. I answered the question. So to build the 3D model, we also used maps of the filling and raising made grounds. So this quarter was previously some islands with filling made grounds that were historically filled, and also there was some raising made grounds that we also have on this island, but also on one other quarter, which is the D quarter here. So for that, we used historical data, maps, photo, borehole descriptions. So here is the results, the 3D model that we developed for the island. So this is the case A. So with the succession of anthropogenic deposits overlying the alluvial deposits and the basement rocks. And so we could also provide thickness maps. And so this was, the model was developed with our GDM tool, and we translated it into ArcGIS layers for the urban developer we were working with, to visualize the types of materials at various depths. So with most questionable made grounds on the surface and mostly sandy ones deeper. So we could also provide some volumes to help anticipate the redevelopment project. So we also compared with the potential pollutions. And so here is another work we did with this a urban historic inventory of all industrial and service activities with potentiality of an index of potential pollution. And if we compare here on the right figure map with the depth of the questionable made grounds, then there is one place here where we have no explanation. We cannot explain the origin of lead due to industrial activity, but we can explain it with the man-made ground map. So both are complementary. So on this first quarter, we had lots of data, and we tried to apply it, and we applied it to other quarters with less data. So here are examples of quarters B and C, and with this L and D is in progress actually. And actually we enriched the typology with the existing the local specificity. So you also could, of course, have an idea of the uncertainty. So if we compare between quarters, the accumulated percentage of each material according to depth, then we can see that we have some specificities in each quarter, and some quarters that are more have more questionable made grounds, are more impacted by questionable made grounds and it's important for them for the urban developer to anticipate this. So we also compared with geochemical data. Here's an example for quarter B. And like in the case of quarter A, we can see an anthropogenic signature in the questionable made grounds, and more or less evident on the various made grounds. What we see nevertheless, especially for organic contaminants, is that when comparing with local background, we also all the materials, all the made grounds, but also the alluvial deposits are impacted, which means that there was also an impact from the industry in this area. So to conclude, so in these cases, the 3D modeling allowed to anticipate pollution issues, but also management of excavated ground. So it appears useful at the various stages of the redevelopment project. It was used at the early in the planning stage, but also in the operational stage. We of course faced some difficulties, like borehole data interpretation from the existing ones, and also the anthropogenic deposits. They have spatial interest in heterogeneity. The logic of deposition is not known, and we also face limits of interpolation due to this. And so some perspectives is the need of a common internationally agreed terms to describe anthropogenic deposits. We also need to improve anthropogenic deposition spatialization, historical knowledge, urban geophysics, interpolation from quarter to city scale. And we also, it would be nice also to trace the excavating materials movements, exportation, importation at quarter to city scale for the dynamic perspective of the geological knowledge. And so I thank you for your attention.
Thank you, Cecile. Thank you very much. Okay. This leads us to our last panelist in our session. Cecile, if you just can you stop sharing your screen, please? Thank you. So the last panelist is Ruven Lenne from Darmstadt City. Can we hear you?
Yes. Can you hear me and can you see the slides?
Yes, we can both. Thank you. It's yours.
Okay. Thanks a lot. So I'm not from Darmstadt City. I'm working for the Geological Survey of the federal state of Hesse. But yeah, we are involved in a project that is addressing Darmstadt, and that's why I wish to report something about the urban geology and its applications for the case study of Darmstadt. So first of all, I need to talk about my personal perception of geology, and also the perception I gained in the last years whenever I talk to people. The first thing, what we see as geologists, is that geology is very, very important. That's good. The civil engineers, they say we can cope with any issue arising from geological conditions. That does mean we do not need to know that much about geology. That's what they often said. The urban planners and the municipalities, they say geology is very complicated and available information mostly some kind of vague and hard to understand. But we would be happy to have useful geological information available. And that's why I personally, why I'm happy that in Norway there are municipal geologists working. That's something new to me, that's interesting. And yeah, I like it. So I think the standing of geology in an urban context, it could be better. And in the end, the question arises, which benefit can be provided by geological information? And that's why I think we need applications. Good. So that's something everybody knows. That's the map showing the development of population for Germany until 2030. The reddish area show a decrease and the bluish area an increase of population. We all know that the urban areas get more and more important, and I would like to draw your attention to this area down there, which is the metropolitan area of Frankfurt, Rhine-Main. That's how it is called. There's some 6 million people living. As the bigger cities, we have Mainz. That's the place I live. Maybe you've heard about it last week when this company BioNTech announced that they invented this corona vaccine. Then we have Wiesbaden. That's the capital of the federal state of Hessen, where my geological survey is located. Everybody might know Frankfurt, and down there, there's Darmstadt. And Darmstadt is a quite dynamic city. I will get back to this later on. Why have we chosen Darmstadt? Because the geological setting, the conditions are very, very complex. What you can see is an image, a screenshot from a 3D model. And we see Darmstadt located up there, surrounded by these reddish rocks. This is the so-called Rotliegend. And this Rotliegend subsided to the west down to around about 2,000 meters below the surface due to this upper Rhine-Graben. And that's where the city is located on top of. It's located on top of the eastern master fault of this upper Rhine-Graben. And that's why we have chosen it, because of its complexity and all the geological phenomena we can investigate. The city itself, as I mentioned, is located right on top of this master fault. We have mountains to the right, which is bedrock, and we have the graben to the left, which is made up of sediments. And a more close but still very general look on geology is something you can see here. We have quaternary, some tertiary sediments in the graben area, while the eastern part is made up of crystalline, of granite diorite, and Permian rocks. Looks not too complicated, but in the end it is. That's something we have found out when we started modeling. We used 1,800 drillings roundabout. A few of them have been available from our drilling database, from the Geological Survey, and the majority came from the city of Darmstadt. And I'm happy for all of you dealing with digital data. We had to digitize data first. So mostly the drillings from the city of Darmstadt have been provided as PDFs. So we had to scan, and we had to stratify and apply this specific key for describing geological deposits for our federal state. And in the end, it turned out that the stratigraphic horizons could not be modeled because of the complexity of information. The drillings are very heterogeneous, and we were not able to identify all the target horizons we would have needed to identify. And that's why we aggregated the data, and that's why we went a step back. So we parameterized the drillings according to the permeability of the specific units. And that's what can be seen here. So the model is covering the upper 30 meters. That's what the city planners say is the important area, thinking of all the work going on in an urban area. And here we have some good information about the permeability, the so-called KF value, which is quite useful. We implemented furthermore some technical infrastructure. So this brown lines, they indicate, or they represent the sewage system, and we put all of it in this 3D model. We made it in 3D object and blended it with the geologic information, which can be seen as a fence diagram here. And we also added the foundations, like it can be seen for the concrete site in the center of the figure. The yellow lines is the power supply, and the blue lines, that's the water supply. And the transparent blue surface, that's a groundwater surface, as it has been given in October 2015. Yeah, and that's another view to this foundation of the concrete site, Darmstadtium, and how we made it part of the geologic volume. The voxels that can be seen are representing the geologic strata, and showing the conductivity or the permeability from blue, very good, to poor, which is more brown. And this information is quite helpful. We have at the moment, we have implemented geologic information, we have implemented hydrogeologic information and technical infrastructure. And from these data, we created some applications, which is the interaction areas between groundwater and the sewage system. That's quite important for the city, as well as the interaction areas between groundwater and foundations. That's also important for BIM. Then we have the permeability in general, and we have infiltration areas. It's interesting to see something about these infiltration areas, because the city is growing from 2010 to 2016 by 11.4%. At the same time, the surface ceiling decreased by 5%. That's what the people in charge told me recently. I think that's quite impressive. And to support this kind of work they are doing every day, we decided to put all this into a 3D database, which in our case is GST, and blended with other data like maps and surface models and things like this. We are able to visualize content through a web browser, and this is some some very useful tool because it supports also some virtual drillings and some cross sections which can be used for reporting or planning, and that's what the city is doing every day. Yeah, but we still have issues. The data interoperability is a big issue. We need to combine our 3D data with 3D models, city models, and we need to visualize this content on also other platforms like ArcGIS, ArcGIS Pro. I really like the approaches done by the TNO in the Netherlands. That looks very, very good. And I think it's worth to also try it for this area. And that's something we are doing at the moment. Good, but we have another topic I wish to get back to, and this is radon. I just saw it on one slide from the presentation in Norway, and it has not been mentioned, but it is very, very important. I think that's a huge chance for geology, for urban geology. You might know that there's a new treaty of the EU Commission. This is the 2013-59 Euratom Treaty, which means that European member states must update radiation protection laws to account for health risk of the exposure to elevated indoor radon levels and prepare national radon action plans. It sounds very, very important. So that's what we did in Germany, and I think that's what every other country in Europe needs to do. And we need to identify radon-prone areas, and those areas show radon concentrations as an annual average in a significant number of buildings with more than 300 becquerel per cubic meter. So this is the number, 300 becquerel per cubic meter. And those areas, they must be determined until the end of this year. And the action required then starts from the 1st of January in 2021. And this action is quite a lot of things to do for those cities or counties which are affected in the end, which will be so-called radon protection areas. And here we start, or we need to get back to geology. I was listening to a lot of anthropogenic issues, anthropogenic deposits, which is very important, but as geologists, we never should forget about the geogenic deposits, which is the geological deposits we have. And there's a lot of radioactivity coming from the rocks. 60% of natural radiation is coming from the elements uranium and thorium. And those elements, they occur with a few parts per million in almost every rock type found in the crystal lattice of certain minerals such as feldspar, zircon, monazite, titanite, and so on. That's what you know as well. And we can differentiate between the concentrations of thorium in blue and uranium in light, bright brownish colors according to the type of rock. So there's the most that can be seen in the granites, and then we have some higher concentrations of thorium in the claystone, while the concentration of uranium is less in the sandstone. But in which way ever, these radionuclides, they are present and they are given. And if we bring this information into the geological maps we have, and again, in the center parts up there, you can see Darmstadt, and you can see that Darmstadt is surrounded by rocks which keep quite a lot of these uranium and thorium contents, depending on the type of rock. The Rotliegend sandstone does have most of the thorium in comparison to the other rocks, diorite, quartz diorite, granite, but also the uranium content is pretty high in the Rotliegend rocks. So this stuff is located up there in the mountains in the eastern part of the city of Darmstadt, but it's going to be dislocated. We have thorium and uranium concentrations coming from geochemical analysis, and this weathered rock is dislocated into the valley, into the graben, and it can be seen, and that's our hypothesis, it can be seen in the 3D models as well. indicated by those sediments which show a higher conductivity, because the grain size of this dislocated material is known as grain cost. It's the so-called, we call it Gruß in German. So we get valuable information from the 3D models, maybe where to go and where to measure radon more detailed than in other parts of such an urban area. We create maps that can be seen to the right that help us to locate those potential areas on the surface. We go there and we measure. Now that's coming from the rocks. And then we have the tectonic features. We have one congress site in Darmstadt, which is the Darmstadtium. And there we have installed a measurement device for microtectonic movements with our colleagues from the Czech Republic. And these microtectonic movements, they indicate that this fault is a recent active fault. So we made a soil gas measurement. We put in some measurement device into the soil, and we derived the number of 340,000 becquerel per cubic meter air, which is soil air in this case. But if we measure the room air right beside, in the building, inside the building, we have some concentration of radon, which is going up to almost 22,000. And this is significantly high. As you know, as you remember, the reference is 300 becquerel per cubic meter. So that's a very important thing to know, because we need to do something about these high radon concentrations. We have other faults in the city. At least these faults are indicated on the geological maps. We do not know precisely their location, their orientation, and their function. Are they active or not? But we can use available information to track it down and to deepen our understanding. And here we have another section, some radon measurements, a radon profile. And as you can see, we have, that's the blue line down there. We have quite high concentrations right on top of the fault, or at least on top of the area where you think the fault is located. This is interesting because we have in many cities, in many urban areas, we have tectonics, and that's the way it is. And it's more important in the Scandinavian countries, more important than in Germany. It might be more important in the Baltic region and the southeastern part of Europe, but we also have the problem in Germany. So the conclusions, the determination of radon protection areas is based on a radon potential map, which is considering geology in a way. And this determination is more statistics, not really sticking to the conditions on site. So, of course, in the end, this radon protection, it's most important where people are living, and this is the urban areas. And we have very high variations of radon concentrations in soil, like we have maybe only limited knowledge about the deposits and the tectonics. And this, to me, is a very big challenge and a chance for the urban geology. And what is the benefit? The remediation of affected buildings, that's about 2 to 4 times more expensive than awareness and prevention. And this is, I mean, I think a good number to get into discussions with people in charge. Yeah, and if you're interested in the study or radon in urban areas in general, get in touch. Thanks a lot.
Thank you, Ruben. Thank you all for your presentations. I think that it was a very interesting webinar. We are getting quite positive feedback, which is great and encouraging for us to continue with similar webinars and actions. If you have any question, feel free to get in touch later. As I can see, all the questions have been answered already online, so we don't have to do this now. I hope you enjoyed this webinar, and I hope that we can meet again in the future during some other future events, hopefully also in person sometimes. So thank you again to all presenters and also to all attendees. I'm sorry again for the small technical problems in the beginning, which shifted the schedule a bit, but I hope that we enjoyed it. Thank you very much, and see you.